In 1955, the United States Navy severed ties with the past and commissioned the USS Forrestal, the world's first true supercarrier. Displacing 81,000 tons, it was a floating city of American steel, designed to project power during the coldest depths of the Cold War. At 1,067 feet long, it was the physical embodiment of a superpower that had recently dismantled the Axis powers and turned its gaze toward Moscow. It carried a tailored air wing of jet-age interceptors, requiring a flight deck surface area never before seen in naval history. 62 years later, in 2017, the Navy commissioned the USS Gerald R. Ford, the most expensive warship ever constructed by human hands. With a price tag of $13 billion, the Ford represents the absolute apex of 21st century naval engineering and nuclear propulsion. It is powered by two A-1B Bechtel marine reactors, generating 3 times the electrical output of the Nimitz class to feed voracious subsystems. It launches 5th-generation stealth fighters using the electromagnetic aircraft launch system, replacing steam pistons with precise magnetic acceleration. Yet, if you apply a laser measure to the hull, you uncover a statistic that defies the logic of technological progression. The beam width at the waterline remains functionally identical to the designs of the mid-20th century, frozen in a state of suspended animation. In 6 decades of absolute global maritime dominance, the physical footprint of the American supercarrier has expanded by less than 4 feet. The length is virtually unchanged, and displacement hit a hard ceiling of 100,000 tons in the 1970s and simply stopped. Consider the industrial context. In that same time frame, commercial container ships expanded their capacity by 1,200%. We transitioned from vacuum tubes to silicon chips, from subsonic propellers to hypersonic glide vehicles, and from analog radios to quantum encryption. Yet the capital ship of the United States Navy, the primary instrument of diplomatic coercion, remains locked in a specific dimensional envelope. Why does a military doctrine predicated on overwhelming force and bigger is better accept this apparent stagnation in hull geometry? Did the Pentagon run out of high-grade steel? Or did the defense budget finally hit a hard limit on ambition? The answer is negative on both counts. The constraints are not financial or political, but strictly physical and infrastructural. The U.S. Navy is not choosing to maintain the 100,000-ton limit out of tradition. They are being held captive by the geometric cage. The adversaries keeping these ships this size are not the Chinese DF-21 ballistic missiles or Russian hypersonic torpedoes. The true enemies of naval expansion are simple physics, immutable geography, and the limitations of industrial concrete poured decades ago. To understand the engineering that rules the waves, we must dissect the invisible walls that confine the most powerful weapon system on Earth. We will analyze why constructing a mega carrier of 150,000 tons is not a display of strength, but a logistical suicide note. We will discover why 100,000 tons is not an arbitrary limit, but a mathematical constant of perfection derived from blood and failure. To understand why the growth stopped, one must first analyze the violent acceleration of the early 20th century carrier evolution. The lineage of the U.S. carrier is defined by rapid, punctuated equilibrium, long periods of silence, broken by sudden, violent leaps in scale. In 1922, the USS Langley, CV-1, was a converted collier ship with a wooden roof, barely capable of generating wind for biplanes. It was a clumsy experiment, a proof of concept that barely hinted at the dominance air power would soon wield over the oceans. World War II shattered the restraints, birthing the Essex-class 36,000 tons of mass-produced aggression that broke the Imperial Japanese Navy. These ships were industrial miracles, but the arrival of the jet age rendered their dimensions obsolete almost overnight. Jets were heavier, faster, and consumed fuel at rates that demanded larger magazines and longer catapult strokes than the Essex could provide. The Navy responded with the Midway class at 64,000 tons, the first American vessels too wide to traverse the Panama Canal locks. This was the first geographic lock broken, a calculated sacrifice of mobility for the necessary raw tonnage of the jet age. Then came the Forrestal in 1955, the quantum leap that defined the modern supercarrier archetype we recognize today. Tonnage spiked from 64,000 to 81,000 tons, and the flight deck was widened to 252 feet to accommodate the revolutionary angled runway. This design allowed for simultaneous launch and recovery operations, a critical capability for sustaining high-intensity combat sorties. However, from the Forrestal in 1955 to the Nimitz in 1975, the length of the vessel grew by a mere 25 feet. From the Nimitz in 1975 to the Ford in 2017, the length grew by virtually zero, revealing a definitive plateau in naval architecture. The hull form of the U.S. supercarrier has been essentially a photocopied design for 70 years, packed with increasingly dense technology. The USS Ford is not a new shape. It is a Forrestal-class hull geometry injected with 21st century digital nervous systems. Why not build a 200,000-ton floating continent capable of carrying 150 jets and remaining unsinkable by conventional weaponry? It sounds like the ultimate strategic asset, a mobile airbase that could dominate an entire hemisphere without land-based support. But if you attempt to construct such a Leviathan, you immediately collide with the concrete womb of Newport News. To see the hard limit of American power, do not look at the Pentagon's budget, but at Dry Dock 12 Inches, Virginia. This is the only location in the Western Hemisphere capable of berthing a nuclear-powered aircraft carrier, and it has finite dimensions. Dry Dock 12 is a massive reinforced concrete pit, measuring 2,172 feet in length and, critically, 249 feet in width. Memorize that number. 249 feet is the hard industrial limit of the United States naval construction capacity. Now, examine the specifications of the USS Gerald R. Ford. Its flight deck width is listed at 256 feet. The mathematics seem impossible. The ship is physically wider than the reinforced concrete hole it is manufactured in. The Navy circumvents this physical paradox by cheating physics, utilizing a structural technique known as the cantilever. The hull of the ship, the displacement volume that actually interacts with the water, is engineered to be only 134 feet wide. This slender foundation allows the massive vessel to slide comfortably into the concrete pit of Dry Dock 12 with room to spare. However, once the construction rises above the waterline, the flight deck flares outward like a massive, steel-reinforced mushroom cap. During assembly, the edges of the Gerald R. Ford literally hang over the concrete walls of the dock and the shipyard service roads. This creates a surreal industrial scene where 100,000 tons of war-fighting machinery looms directly over the heads of shipyard workers. But here's where the cage slams shut. Running parallel to the dry dock is the gantry crane known as Big Blue. Standing as the largest crane in the Western Hemisphere, Big Blue runs on fixed rail tracks positioned dangerously close to the pit. The clearance between the edge of the Ford's flight deck and the structural legs of the crane is measured in inches. If the Navy demanded a carrier with a 300-foot beam, the flight deck would physically smash into the crane's support structure. To build a larger ship, the United States would be forced to demolish and reconstruct the entire industrial foundation of Newport News. You would have to tear up rail lines, widen dry docks, and replace a crane that is itself a marvel of engineering. The cost of this infrastructure overhaul would run into the billions before a single plate of ship steel was ever welded. CVX design studies in the 1990s confirmed this fiscal reality. The infrastructure tax killed the mega carrier before it reached the drawing board. Consequently, the Ford is not the ship the Navy necessarily desires. It is the exact size of the tool used to cast it. But even if we spent the billions to build a larger dock and a 200,000-ton Titan, we would only be building a prisoner. Aircraft carriers are instruments of global maneuver, and true strategic freedom requires the ability to transit the world's maritime choke points. For a vessel with a 40-foot draft and the height of a 25-story building, the world's oceans are a treacherous maze. The most critical bottleneck in the global security architecture is the Suez Canal, the jugular vein connecting Europe to the Indo-Pacific. If a carrier cannot transit Suez, it is forced to circumnavigate the African continent, adding weeks to critical response times. This detour burns millions in logistics and, more importantly, consumes the finite operational lifespan of the ship's nuclear reactor cores. The Suez Canal Authority maintains strict regulations. The maximum allowable beam for transit is currently set at 254 feet. The USS Ford, with its 256-foot flight deck, is already pushing the absolute legal and physical limits of international maritime law. While the hull fits the underwater channel, the flight deck literally overhangs the canal's desert banks during the transit. This creates a massive aerodynamic sail area. A sudden gust of desert wind can exert enough force to push the ship aground. Pilots do not simply steer the carrier. They fight a constant battle against physics to prevent the ship from drifting into the sand. But the horizontal cage is only half the problem. The mega carrier must also contend with the vertical ceiling of global infrastructure. Spanning the Suez Canal is the Al Salam Bridge, which provides a fixed vertical clearance of exactly 230 feet above the waterline. On older vessels, the Navy utilized folding masts to duck under such obstacles, but the Ford represents a shift in sensor philosophy. It carries the dual-band radar, a massive array of sensitive panels that require a rigid, vibration-free foundation to track hypersonic threats. These radar panels cannot be folded or tilted. They must remain perfectly aligned to maintain the ship's eyes on the horizon. Therefore, the integrated mast was sculpted with agonizing precision to clear the Al Salam Bridge by a margin of mere inches. Imagine piloting a 100,000-ton fortress under a concrete beam at 10 knots while the tide fluctuates beneath your keel. A single calculation error or an unexpected surge in water level wouldn't just clip an antenna, it would decapitate the ship's brain. The Ford fits through the Suez, but it fits with the terrifying, zero-tolerance precision of a bullet sliding into a chamber. If the ship were any larger, it would be geographically lobotomized, unable to move between the world's two most critical combat theaters. The cage tightens even further when the ship attempts to return to its home port at Naval Station Norfolk. We must talk about the silent enemy of the deep draft Navy, the constant accumulation of underwater mud and silt. The access channels at Norfolk are maintained at 50 feet, but nature relentlessly fills these paths at 2 feet per year. The Army Corps of Engineers is locked in a permanent, 24/7 dredging operation just to keep the Atlantic Fleet from being grounded. If we constructed a 150,000-ton ultra-carrier, its displacement would force it to ride significantly lower in the water column. A draft exceeding 45 feet would effectively eliminate the safety margin, forcing the ship to drag its belly through the harbor mud. Such a vessel could never enter Norfolk or Yokosuka. It would be a homeless king, forced to anchor miles offshore. Relying on smaller ferry boats for every resupply mission and personnel transfer would turn a strategic asset into a logistical liability. The Earth itself has dictated the terms of American naval power. 100,000 tons is the maximum weight the planet's geography permits. Critics often dismiss these physical constraints, arguing that the need for raw firepower outweighs the inconvenience of docking or transiting. They envision a deck carrying 120 aircraft, believing that more planes automatically translate to a more lethal weapon system. This is the big box retail fallacy of warfare. In high-end naval combat, buying in bulk creates diminishing marginal returns. In the 1990s, the Navy and the Rand Corporation conducted extensive simulations on mega-carrier flight deck dynamics. They discovered a shocking ceiling. A flight deck is a finite ecosystem of roughly 4.5 acres that quickly reaches saturation. If you jam 120 aircraft onto a single deck, you don't create a more powerful strike force, you create a floating parking lot. On an oversaturated deck, aircraft must be shuffled like a sliding tile puzzle just to allow a single jet to reach a taxiway. When parking density exceeds the operational threshold, the bomb farm becomes inaccessible and catapult cycles begin to lag. The critical metric that defines a carrier's lethality is not its storage capacity, but its sortie generation rate, or SGR. SGR measures how many fully armed combat missions a vessel can launch and recover within a standard 24-hour window. While a Nimitz-class carrier sustains 120 sorties per day, the Ford targets 160, a 33% increase in combat power. The Navy achieved this surge not by expanding the hull's volume, but by re-engineering the flight deck's internal pit stop logic. They analyzed the deck through the lens of a NASCAR pit crew, identifying every second wasted in the movement of ordnance. On the legacy Nimitz class, the bomb farm was positioned in a central location that required crossing active aircraft taxiways. This meant that to load a precision-guided bomb, crews had to push carts through a lethal gauntlet of jet exhaust and moving wings. On the Ford, the island superstructure was shifted 140 feet aft and narrowed, opening up a massive pit row area. They installed Advanced Weapons Elevators, AWE, which utilize linear electromagnetic motors to move ordnance at twice the speed of cables. These elevators deliver munitions directly from the deep magazines to the aircraft refueling stations, completely bypassing the taxiways. This creates a closed loop of violence where a jet can land, refuel, rearm, and launch without ever obstructing another aircraft. The Ford generates superior combat effects compared to a hypothetical 150,000-ton monster because it prioritizes density over raw volume. It is the triumph of efficiency over excess, proving that a refined 100,000-ton platform is more dangerous than an unrefined Titan. Yet, the seductive whisper of the Super Titan persisted in the Pentagon, leading to a darker realization regarding survivability. Beyond the engineering hurdles and the Suez bottlenecks lies the most terrifying argument against the megacarrier: strategic suicide. A 150,000-ton ultra-carrier would represent a concentration of national power so immense that its loss would be a catastrophic defeat. Such a vessel would cost roughly $25 billion, carry 6,000 personnel, and house 25% of the fleet's air power. In the age of hypersonic cruise missiles and long-range wake-homing torpedoes, putting all your eggs in one basket is a strategic sin. If a single carrier killer missile slips through the Aegis screen, the United States hasn't just lost a ship, it has lost the war. Naval planners realize that dispersion is survival, while concentration is death in the modern anti-access, area denial environment. The Navy would rather deploy 11 100,000-ton fighters across the globe than 6 fat targets waiting to be hunted by the enemy. This is the Goldilocks zone of naval architecture, a weight class that is small enough to be nimble but large enough to be devastating. To move beyond 100,000 tons would be to ignore the harsh lessons of the battleship era, where size eventually became a vulnerability. The USS Ford is the culmination of a century of sweat, blood, and mathematical refinement. It is the number of perfection. It fits our docks, it squeezes through the canal, and it rides just high enough to avoid the mud of our home harbors. We did not choose a limit, we discovered a balance that allows the United States to project power to any shore on Earth. We innovated inside the hull with electromagnetic catapults and digital controls, rather than bloating the external dimensions of the ship. In a world obsessed with more, the Navy learned that enough is the most dangerous and effective word in the military dictionary. Too much tonnage makes a vessel a target. Precision and speed make it a weapon that can survive the 21st century. The Ford is a masterpiece of constrained engineering, a ship that thrives precisely because it respects the limits of the cage. This is the doctrine of the U.S. Navy decoded. Not the biggest ship possible, but the most efficient ship allowable by reality. When you see the Ford on the horizon, do not look for growth in feet or inches. Look for the density of its lethality. It is a cast of a mold designed by geography, physics, and the sheer will to dominate the global commons indefinitely. Every weld and every circuit is a testament to an industrial base that knows exactly how to walk the tightrope of power. The cage isn't a prison, it is a framework that forces us to be smarter, faster, and more innovative than our rivals. While others dream of bigger hulls, the United States has mastered the art of the perfect 100,000-ton strike platform. This is the ultimate machine, a system that fits perfectly within the terrifyingly narrow corridors of global strategy. And that is the objective truth we hunt for here. We strip away the myth to find the cold logic of the machine. If you believe that American engineering is the cornerstone of global stability, acknowledge the power of the 100,000-ton limit. The evolution from the coal-burning Langley to the nuclear-powered Ford is a journey of increasing intelligence, not just increasing mass. We have reached the apex of the supercarrier's physical form. The next revolutions will happen in the invisible realms of data. Lasers, drone swarms, and artificial intelligence will fill this 100,000-ton shell, making it more potent with every passing decade. The geometric cage has done its job. It has forced the Navy to stop growing out and start growing up in capability. Stay ready for the next shift in the global balance of power, where the limits of concrete will meet the unlimited potential of tech. Our analysis continues to tear apart the blueprints of the world's most sophisticated weapons to see how they truly function. Information is the first line of defense. Understanding the physical constraints of our fleet is essential to understanding our security. Subscribe now to join the elite group of analysts who look past the headlines and into the hardware that rules the waves. This is Navy Decoded. We are signing off, but the watch continues. Stay dangerous, stay informed, and respect the cage. Beyond the steel and the mud, the final lock on the geometric cage is the human element, the cognitive load of command. Managing a crew of 6,000 souls within a 1,000-foot hull is already an exercise in the extreme limits of social engineering. If we built the 200,000-ton Leviathan, the internal logistics of simply feeding and moving the crew would collapse under its own weight. You would need internal transit systems, high-speed elevators, and a command hierarchy so complex it would stifle tactical decisiveness. The 100,000-ton carrier represents the maximum scale at which a single human commander can maintain total situational awareness of their deck. This is why the Ford's island is smaller and pushed further back. It's about clearing the commander's literal and figurative field of vision. Every foot of growth beyond this point introduces a complexity tax that no amount of nuclear power can ever hope to pay. Look at the history of the Great Ship Syndrome, from the Vasa to the Titanic, and the gargantuan battleships of the 1940s. History is a graveyard of vessels that tried to outgrow the physical reality of their era, only to be consumed by it. The United States Navy has avoided this trap by pivoting toward network-centric warfare rather than hull-centric warfare. The carrier is no longer just a ship. It is a node in a distributed planetary-scale system of sensors and shooters. By keeping the ship at 100,000 tons, we ensure it remains compatible with the world's existing naval infrastructure for the next 50 years. We are not waiting for a bigger dock. We are building a smarter fleet that doesn't need one to win the next conflict. The Ford's real power isn't in its displacement, but in its ability to surge 30% more sorties than any rival on Earth. In the cold calculus of the Pacific, or the narrow waters of the Persian Gulf, that 30% is the margin of victory. It is the difference between an intercepted strike and a target destroyed, between a superpower and a former world power. The geometric cage isn't a sign of American decline, but a testament to American strategic maturity and industrial discipline. We have mastered the medium of the supercarrier so completely that we no longer need to change its shape to increase its lethality. While other nations struggle to launch their first 80,000-ton carriers, the U.S. Navy is already iterating on the third generation of perfection. The Ford-class will rule the waves well into the 2070s, a design frozen in time, but evolving at the speed of light. This is the result of a culture that respects the laws of physics as much as it respects the mandate of global dominance. We have explored the blueprints, decoded the logistics, and faced the reality of the mud and the concrete that define our power. The next time a critic asks why the carriers aren't getting bigger, tell them they are looking at the wrong set of numbers. Don't look at the length, look at the kilowatts. Don't look at the beam, look at the sortie rate per hour. The future of naval power is dense, efficient, and perfectly sized to fit the narrow gates of global maritime strategy. We have reached the edge of the cage, and instead of breaking the bars, we have turned the cage into a fortress. This is the final chapter in the story of the supercarrier's physical growth, but the first chapter of its digital supremacy. The United States Navy remains the undisputed master of the 100,000-ton limit, a number that will hold the line for a century. Thank you for joining us on this deep dive into the engineering that sustains the big stick of American global diplomacy. If you found this analysis insightful, make sure to engage with the algorithm to ensure this intelligence reaches those who need it. Share this with those who believe bigger is always better, and show them the power of constrained, precise, and lethal engineering. Our next investigation will take us into the silent world of nuclear submarine evolution. Make sure your notifications are turned on. The ocean is a harsh mistress, but to those who decode its secrets, it is the ultimate high ground of geopolitical influence. From the drafting tables of Newport News to the bridges of the Fifth Fleet, the mission remains the same: remain ready. The blueprints have been torn apart, the secrets revealed, and the logic of the 100,000-ton carrier is now yours to command. Intelligence is the force multiplier that turns a standard weapon into an unstoppable system of national survival and dominance. We are the watchers of the fleet, the decoders of the machine, and the narrators of the power that rules the global commons. The geometric cage is locked, the limits are set, and the Ford is currently on station, ready to answer the call. Respect the physics, trust the engineering, and never underestimate the discipline required to maintain the perfect balance of force. This has been Navy Decoded. Stay ready, stay dangerous, and above all, stay informed on the hardware of the hegemony. Final graphic: USS Ford silhouette over a 100,000-ton marker. End audio: low-frequency hum fading into sonar pings. Outro: type power in the comments if you stand with the engineers of the fleet. Screen fade to black.